this is lecture number 9. And I thought to spend a few minutes on something which I think is appropriate for us to do after talking about electromagnetic waves propagating in a conductor. So it reminds me something about conductor. And you may remember that we have always been told that if you place a free charge inside a conductor, then it would flow to the boundary, it would go away to the boundary. And I would like to demonstrate that is, well, true. I mean, it's got to be true in view of what I'm going to show you in a few minutes. Let's start with the conservation of free charge. So we have d rho free by dt plus the divergence of the free current equals 0. And free current here, of course, we are inside a conductor. We are talking about the conducting current. Conducting current, of course, is related to the electric field E and the conductivity. That. So that we can write this as divergence of sigma, the conductivity, and the electric field E. But you also recall that the electric field E is related to the electric displacement D by D divided by the permittivity. So that this is equal to divergence of sigma over permittivity D. Now let's talk about a homogeneous conductor. So that sigma over epsilon being space independent, so that I can take this out to the left of this operator, the gradient operator. So this would be sigma over epsilon divergence of D. And now you remember, the first Maxwell's equation, in matter, inside matter, says that the divergence of D is nothing but the free charge density. So that if you put this back into this conservation equation, we arrive at d rho f by dt plus, the sign is important, plus sigma over epsilon rho f. And of course, it has to be, actually, let me do it here. D by dt rho at r at time t plus this is rho at location t and time t is equal to 0. So, there's a simple equation, and the solution is rho at a fixed location. Let's talk about fixed location R. Then you have the charge density as a function of time will be equal to, well, exponentially, goes as e to the, this goes to the other side, is minus sigma over epsilon t. So that at time 0, the charge density is rho at that location, time 0. So that you see that, if you put a free charge at the location R at time 0, it will die off. It will, the charge density later on at the location would go to 0. So where has that charge gone? Well, goes away to as far as it could, namely to the boundary. So that shows that indeed, you cannot, well, unless you really do something to keep the free charge there, otherwise it would goes away as time passes. Right. All right, so this is something that I thought about. This, I thought it's useful to know. So let's erase this, and then start on a certain topic, which is not unrelated to what we talked about in the last lecture. You remember in the last lecture, we talked about electromagnetic waves propagating inside conductor. And we saw in that case that, in fact, the speed of propagation of the waves, V, in fact, depends on frequency. Since the index of refraction is inversely proportional to the speed, so that the index of refraction is a function of omega. In fact, we found out more. We've also found out that the permittivity is a function of omega also, as a function of frequency, knowing that, in fact, it is effectively complex. Effectively complex. And since a wave number for a wave with frequency omega is given by square root of epsilon mu times omega, if the permittivity is dependent on omega, but then k of course would depend on omega. And it would, since this permittivity is complex, so k, the wave number, is complex. So now in the conductor case, we wrote k is equal to k plus I k minus. The k plus refers to the real part of k, and the k minus refers to the imaginary part. And this imaginary part implies that, in fact, the wave would attenuate away as a function of position of propagation. Today, in this lecture, lecture 9, which in fact you can find in Griffith's 4th edition, section 9.4.3. So we are not talking about things in chapter 9. And we are going to be talking about propagation of electromagnetic waves in a dielectric medium. We will show you that, in fact, just as in the conducting case, in the dielectric medium, K, the wave number, also become complex. And that the permittivity is complex. And it's a function of frequency. And therefore, N is also depends on frequency. That the index of refraction depends on frequency should come as no surprise. After all, you recall the famous demonstration by Isaac Newton, who used a prism to show that, in fact, blue light got bent much more, bent more than red light. So that, but this phenomenon of light being bent by different amount depending on frequency is known as the phenomenon of dispersion. If index of refraction N depends on omega, so that obviously this speed of propagation V is also depends upon omega. And and by extension, nowadays people say that whenever you have a medium which supports propagation of a wave whose speed depends upon frequency, we say that that medium is dispersive. And we'll show you, we know that already. Conductors are dispersive medium. And we'll show that, in fact, the electric medium is also a dispersive medium. All right? Let's see how that can be shown. And we need a certain model to describe the physics. Well, as I promised you, we will be using, we will come back to that model, when we introduce conductivity, remember, again. Except that this time, we are talking about, a dielectric medium, so we will be talking about particles being bound inside molecules. So let me start by, writing down the model. Let's say that I have a charge Q, mass M, in the presence of a certain external force, which we are going to take that as coming from electric field E. This charge moves with velocity v, but it's being opposed by a certain resistive force. And so let's write it down again, the model. The equation of motion for this charge is given by mass times acceleration, that's the force, and the acceleration, I will write that as, instead of dv by dt, I will write that as d square r by dt squared. And that's equal to, the force, due to the presence of electric field E, it would be QE. And the resistive force, you remember, is minus m gamma v. V is dr by dt. That was the model we introduced to discuss conductivity. But now we are talking about this charge being one of the charges bound inside certain molecule. And how do you bound the charge? By means of certain force. And for that force, we are going to take, for this model, we are assuming it to be harmonic force. So it's equal to minus m omega naught squared r. Well, omega naught is the natural frequency for that particular charge inside the molecule that we're talking about. All right? So, and it will turn out that this model is very simple, obviously, is surprisingly correct. So it's not a bad model to talk about. All right? So let us take the electric field E to be time dependent with harmonic time dependence. So let's use E naught e to the minus I omega t. Notice that this omega is the frequency associated with the external field, nothing to do with this intrinsic frequency for this particular electron inside our molecule. All right. And at this point, let me move these two terms to the right, to the left rather, and let me also divide out mass m. Divide it out, divide it out, divide it out, so that I have to put over mass in the last term, and put this to the other side, become plus. Plus equals. All right. Now this is the equation to solve for R. Okay. And since the driving force depends on time in this manner, so that you will expect that in the steady state, R will settle to have the same harmonic dependence of time. So that you expect in steady state, R will go like e to the minus I omega for its time dependence. That's a useful observation, because if that is the case, then d by dt acting on this will just bring down a factor of minus I omega. So this will become a simple algebraic equation. You don't even have to solve for the differential equation. All right, so let's do that. So here, you have to take the derivative twice. So each time brings down a factor of minus I omega, so that minus minus cancel. I is minus, so minus omega squared. Times R. And times, then this, let's see, then this term, let me do this term first, plus gamma. Let me put gamma not here instead of gamma, because later on we are going to generalize the whole thing, not just talk about one charge, but all the charges inside the molecule. So we are going to label them, put them into classes, into groups. Group I, will have natural frequency omega sub I, and this dampened coefficient gamma I, etc. All right, so call this gamma naught for the time being, and this is multiplied by minus I omega. And then this, of course, is just as it was, plus omega naught squared. And this is R. And it's given by as Q over M times the H of U. Now this is a simple algebraic equation. We can solve for R right away. R is equal to Q over M E, let me put it here, divided by this. So it's omega naught squared minus omega squared minus I gamma naught omega. And if I'm not made a mistake in algebra, I think I'm correct. Then that's the result you get for this one particle, one charge inside a certain molecule in the dielectric medium that we're talking about. Let's say that inside molecule there are Fi electrons with intrinsic frequency omega I, and with the dampened coefficient being gamma I. And let's say that there are n molecules per unit volume. Then, I forgot, not yet, sorry. In this expression, they multiply by Q. It's Q squared. QR, of course, is nothing but the electric double moment of that electron. So this is P, electric dipole. So that, let's add up the electric dipole moment for that molecule. Then multiply by the number of molecules. Then we will find out the total electric dipole moment per unit volume. which of course is the P, polarization. So polarization is equal to, number of molecules per volume, and you have, and that is a factor of Q squared over M, which is, common factor, so I can do that. And now I have to sum over the contributions from those different classes of electrons. And there are Fi of them in the ith group, and each one contributes that much, divided by omega, now change notation from naught to I, minus omega squared, plus minus I, gamma I, omega. Have I got everything? Yes. Right. So Q squared over M, N is the number of molecules per unit volume. Fi being the number of electrons in the ith group inside one molecule. And then I have this come here. Correct. Oh, I'm sorry. I still have the E. Electrofield E. Let me multiply this by epsilon naught, and at the same time divide it by epsilon naught, and name it a bracket around this. You may recall that polarization P is given by, is also can be written as epsilon naught times the electric susceptibility of the medium, times E. And that's why I put the epsilon naught outside already, so that you can now identify what's inside the square bracket as the electric susceptibility of this dielectric medium we are talking about. So let me copy that down. So chi E is equal to NQ squared over M epsilon naught, summing over those different types of electrons inside a molecule. There are Fi of them inside omega I squared minus omega squared minus I gamma I omega. And you can also, once you note the electric susceptibility, then you can write down the permittivity of this medium, epsilon. You remember it's equal to epsilon naught times 1 plus the electric susceptibility. So that the permittivity for this dielectric medium that we are talking about is equal to epsilon naught 1 plus this NQ squared divided by M epsilon naught sum over I of Fi divided by omega I squared minus omega squared minus I gamma I omega. It's that. Now it's obvious that the permittivity is frequency dependent. That's number one observation. Number two is that this permittivity is complex. So frequency dependent and it's complex. And its complexity, the fact that it's complex, would being something very interesting. And let me make use of this. So let's again talk about an electric wave, electric field electromagnetic field propagating inside the medium under consideration. With wave number k and frequency omega. Then you remember that the wave number is equal to, is related to the frequency by epsilon mu square root times omega. Now that the permittivity is complex, that means that automatically K is complex. And so let's write this as square root of epsilon divided by square root of epsilon naught. And for almost all the materials, the permeability is more or less equal to the permeability for vacuum. So may I just approximate it by this? So that if I have omega, and then there's this mu naught here, so there's extra this, so mu naught epsilon naught. Right. And this, of course, is nothing but 1 over c. So the k is equal to omega over c times square root of the complex permittivity divided by epsilon naught. So now, k is complex, and let me write down the real part and real imaginary part. And for the conductivity case, we use k plus to stand for the real part, and k minus for the imaginary part, because of the fact that those two cases look so similar, except for the sign of the thing plus or minus 1. One is corresponds to plus 1, one corresponds to minus 1 inside the square root or something. But now, let me in fact use subscript r to stand for the real part of k, and subscript I for the imaginary part of k. Please, this r does not stand, this case of r does not stand for the wave number for the reflected wave. This I doesn't mean the instant, refer to the instant wave whatsoever. This stands for real. This stands for imaginary. I hope there's no confusion. In the notes, I think I still use k plus k minus, but you may find it confusing. Although you may also find it confusing to use R and I. R stands for real, I stand for imaginary. Instead R stands for the reflected beam, reflected wave, and I stand for the incident wave. Anyway, that's what it is. All right, so K is given by square root of this ratio. Well, this permittivity is given here. It's very messy, so it's very hard to take the square root. But let us talk about a case where we can do things easily. That would be the case if this is small compared to 1. Then I can use theta expansion. So I'm introducing 1 plus something small, delta. That would be, well, delta is much less than 1. Is 1 plus 1 half delta. So we do not do work with square root of this complicated thing. But instead, it's now 1 plus 1 half of that. That obviously would be the case for the case if the directional medium is some kind of gas, for example. But in that case, let's work things out for a medium for which this is small compared to 1. Then things will become much simpler. All right? Okay. So let me write down K first. K is omega of c times square root of this epsilon, divided by epsilon naught. Good. Cancel this out. So as I said, so it's this. 1 plus 1/2 of this, which is nq squared over m epsilon naught. And then complicated summation over this fi divided by omega I squared minus omega squared minus I gamma I times omega. Now, obviously, k is complex, and k depends on, divided by omega. Well, we move this to the other side. Still depends on omega. So the speed of propagation, is, well, depends on omega. So again, the medium is dispersive. All right? I should write down roughly, and that's because I've made a tail expansion. All right? To identify the real and imaginary part of this complex quantity, we have to take a look at what's inside here. This is simple. All we have to do is multiply both upstairs and downstairs by this plus I gamma omega. All right? So let's do that. May I do that? Well, let's do it here. So we rationalize this. So this becomes fi times, we have omega I squared minus omega squared plus I gamma I omega divided by this times that, of course, the cos term comes out, that's the whole point. So that there's no imaginary quantity in the denominator. Now, so there's omega I squared minus omega squared squared. And that, this times that, minus I times I will be plus 1. So plus gamma I squared omega squared. So that now we can obviously get rid of the real part as that, the imaginary part as that. So that, let's now write down the result. I think I can erase this. So that k plus the real part, is equal to omega over c times 1, of course it's real, so got to be included. Plus 1/2 times nq squared divided by m epsilon naught, summation over I, now fi times that, fi times omega I squared minus omega squared divided by that denominator, omega I square minus omega square square plus gamma I square omega square. That's the real part. And the imaginary part is equal to this times that. So again, omega over c, no contribution from 1, so this 1/2 n q squared over m epsilon naught sum over I of Fi, gamma I omega. Fi gamma I omega divided by this denominator. Omega I square minus omega square plus gamma I square omega square. That's it. And as I told you, I tend to make algebraic mistakes. So let me take a peek at my lecture notes to make sure that I've not omitted anything. Okay, good. Thought I missed that one. So far, so good. K minus. Oop. Let's see. There's something funny. Oh, there's omega here. Oh, scared me for a moment. That's correct. I can put this omega outside. Let me do that. Look. Omega square. Ooh. And, correct. I didn't make a mistake. That's unusual. All right. So now let's write down, the electric field E propagating in this medium. Again, let's assume that it's propagating towards the positive x direction. So that E is given by E raised to the not to the e to the I k x minus omega t. Okay, and now I have k is given by the real part k real plus I k imaginary, so that I can pull out this e to the I minus k I x. So that is attenuation of the wave again. And then now we have e to the I k real x minus omega t. So this part represents the propagating wave, and this factor denotes the amplitude being attenuated. Now, since the intensity of the wave is proportional to E squared, and therefore will be proportional to the square of this, proportional E to the minus 2 kIx. It's customary for this discussion to call this multiplied x in exponent, denoted by I think Griffiths used the notation alpha, I used to anyway, and this is known as the absorption coefficient. It tells you how fast the energy will be attenuated away as the wave propagates towards larger x. So that alpha is just twice that. So may I just use my green pen to multiply by 2 to get alpha. Alpha is equal to that cancels this one half. Is that. And then k real is here. And let's see, let me go. So N is C over V. V this omega over k plus k plus. So this is equal to k plus MC over omega. So that the index of refraction would be really, oh, k plus, k sub r doesn't mean the real part. I'm so used to the notation k plus as the real part. So, okay, let me write down n, and index of refraction is equal to c times omega, okay, c over omega times kr. Okay, when c omega cancel this, so it's that. So that the index of refraction is given by this, whereas alpha is given by that. Okay, what's next? All right. Let me use this sliding door, sliding blackboard to continue. And erase this, I think we're done. With this. All right, let's take a look at n is given this index of refraction, and alpha is given by this. Okay. This gap is gone. And this half is gone. All right. Now, when the frequency is far away from any of those resonant frequencies. So this will be big, and this term is relatively small compared to that. So the away from resonant frequencies, this term is negligible. Okay. But as frequency, if you are talking about frequency, very close to one of the resonant frequencies, the omega i's, this will be small, and this, of course, will be important. Okay, so let me, in fact, roughly make a plot, as a function of omega, concentrating, on one particular, resonance frequency, say omega j here, a resonant frequency. So as a first approximation, I can just talk about in this summation. I will forget about the rest. I'll come back to this one. Just keep the jth term, and you can see that. You can see that. Let me put this n1 to the other side, so that's to be n minus 1. Put this n to the outside, so minus 1. So this is n minus 1. And let's plot n minus 1. Keep it only the jth term here. All right? As omega approaches omega j from a smaller omega, and you can see that n minus 1 goes up. So the frequency, the index of refraction, increases as with omega, which is what we have found. So that's natural. On the other hand, when omega is equal to omega I, this is 0. So that somewhere, so that this curve for n minus 1 eventually going to turn down so as to hit 0, and omega equals omega j. So this goes this way, and this falls sharply, and we come back. So that in this region, okay, and okay, changes rapidly with omega. Okay. So that you have, for this region, you have okay, large okay, dn by d omega. Not only that, okay, you see that n minus 1 is 0 here, then it's below 0. That means that n would be less than 1. If it's less than 1, does it mean that in fact, okay, the light, the wave propagates with speed larger than speed of light c in vacuum? The situation is more complicated. Okay, for one thing, okay, we have so far in this concentrating on only the j term. Of course, you could add up contributions from the other resonances also. That will change the story. That's point number 1. But let's and I will come back to point number 2 later. Okay, this region where n is a decreasing function of frequency is atypical, not typical at all. Because typical situations that index of reflection rises as with omega. So this region in which n goes down with frequency is known as the region of anomalous Is that how it's spelled? Dispersion. It's abnormal. So it's anomalous. And you can also take a look at the result for the absorption coefficient. Again, concentrating just on the particular term, the j term, then you see that in fact alpha, and let's use blue, it goes up and then reaches the maximum at the resonance. So that at the resonance, the absorption coefficient is large. In fact, it's so large that the medium in this region of the frequency range become more or less opaque. All right. So let's this is discussed in Griffith's 4th edition, section 9.4.3. Let me take a sip of water. Now let's go on to talk about another topic, which is related to what we're talking here. And before I do that, I almost forgot. So let's write down. Can you erase this now? Let's write down n minus 1 for omega far from any of the resonances. And then, obviously, far enough from any resonances, then of course, this damping term will be small compared to this, so that we can ignore it. Then it becomes 1/2 nq squared over m epsilon naught, sum over I, fi omega I squared minus omega. Oh, sorry. Once we can neglect this damping term, then this cancels one factor of that. So it's divided by square of omega I squared minus omega squared. Now, for most transparent media, the first important resonant point lies in a frequency something like in the ultraviolet region. So that normally we will we talk about those light with frequency less than that resonant frequency. So that this is positive. So that n minus 1 is positive. So n is greater than 1, as I said. All right? So much for this discussion on the propagation of electromagnetic waves inside a dielectric medium. Okay, I'll come back to this. I can erase all this now. Oops, okay, I should keep that. So far, we've been talking about harmonic waves with one single frequency. But of course, well, we have been doing that for good reason, because all functions can be, from the study of Fourier analysis, can be written as linear combination of all those harmonic terms. But if you really stick with a harmonic wave with one frequency, then what you see is that wave just repeat itself on and on all the time. That's the same. It looks the same all the time, and it goes on, and it conveys no information aside from the fact that you know that it is there. But if you want to have some information sent from one location to a distant observer, you need to do something about the wave so as to be able to encode the message in that pulse of waves. And so that the remote observer can decode it and get a message. And the way to do that would be, in fact, I'll talk about it, to send a pulse. Containing the information. But to start, let's use one harmonic wave involving one single frequency does not suffice to send information. So let's, in fact, talk about two such waves. So let me talk about psi 1 as function of x and time. Again, talking about the propagation along x direction. Let's say that it has amplitude A, and we use the sinusoidal wave, cosine of k1x minus omega 1t. And let's talk about another wave, psi 2. And for convenience of discussion, let us say that that wave has the same amplitude A, but with a different wave number, we call it K2, and a different frequency, call that omega 2t. And we're interested in the superposition of these two waves propagating towards positive x direction. So that we have this plus that. So that that's why now I want to talk about same amplitude. So that what I'll be talking about will be just cosine this plus that. We know that cosine let me not call it A, B plus cosine C, that can be written as the product of cosines with a factor 2 times cosine of, okay, the average of B and C, and cosine of B minus C 1/2. So that, okay, the total wave from the superposition of both of this is given by 2a cosine of, okay, let me call, okay, k1 plus k2 half of it to be, okay, k average, and omega 1 plus omega 2 divided 2 to be omega average, whereas k1 minus k2, yes, I will call this k sub mod. Mod stands for modulation. And it comes about because we want to modulate a wave so as to be able to send a message, to encode a message. Encode omega 1 minus omega 2 half to be k omega mod. Notice that k1 plus k2, let's talk about k1 and k2, okay, close by, and omega 1 and omega 2 close by. So that we see that this, okay, the average value is much greater than the mod value. Okay, small, this is small compared to this. Small, okay, wave number correspond to long wavelength. So that, okay, I will have, let me write it down first, so that I have, okay, cosine, okay, let me use different color. K average x minus omega average t and multiplied by cosine of k mod x minus omega mod t. So that the wave function is given by, okay, the product of two sinusoidal wave. Okay. And, oh, sorry, should I use green? That's the whole point. Okay. I use red. So k mod x minus omega mod t. So what does this wave look like? Right, it will look like this. Namely that, okay, let me plot this, the mod part, okay, it involves, okay, a longer wavelength. So this is like that. Let me draw it as that. And this part, green part, is the average one. Okay, involves, okay, shorter wavelength. Okay, but okay, just multiply by this so that, okay, cosine cannot be going, okay, beyond value of this. Since the maximum value of cosine is this one, so that, okay, this part, okay, superimposed on this will be like this. So that this green part referring to, okay, wave with, okay, shorter wavelength, okay, propagating, okay, bounded by this envelope, okay, of modulated wave. Okay? Let's now imagine that K1 and K2 are infinitesimally, okay, off. They're different, but by an infinitesimally small, okay, value. Similarly for omega 1 and omega 2. So that we call this this is delta K, and this is delta omega, and this is just the average omega, this is called omega, this is K. Okay. So for the case of K1 roughly equal to K2, omega 1 roughly equal to omega 2, then we have the wave n equal to 2n cosine of kx minus omega t, and multiplied by this. Oh, I forgot. Green part, green, multiplied by cosine of the red part, which is now delta k x minus delta omega t. So the wave is given by product of these two. And these two factors represent propagation waves with different speed. From this, because the green wave propagates with a speed v, which is given by omega over k. Whereas the modulated envelope wave is the red part. This gives rise to a velocity equal to delta omega over delta k. And if the two k's and two omegas are really extremely close by, only differ by infinitesimal amount, so this would be d omega by dk. So there are two different speeds. One is to do with the green part, red one, the red part. And we call this velocity to be the phase velocity. Phase velocity. And this we call denoted by V sub group. And this is the group velocity. It's called group velocity because inside each of the red curve, there's a group of small oscillation waves. Hence the term group. I'm going to show you very soon that the velocity, which makes more physical sense in terms of physics, is the group velocity. Namely that, we want the group velocity to be not to exceed speed of light in vacuum C. Whereas this phase velocity, it's just a phase velocity, it can be greater than speed of light. And I will give an example next time. That's the case. But before that, doing that, I have to show you that group velocity, in fact, is the velocity that we would like to use, because as I will show you, that is the velocity with which we can transport energy. Of course, energy can be used to contain information. So that this is the velocity that gives a bound to the speed of propagation of information. That's what's important. And we want that, we will be, will not feel easy if that is larger than speed of light in vacuum. But the situation actually is much more involved than that. But roughly speaking, that's the case. And it goes beyond the scope of this course, to dig into the detail, into behavior like this. the physics in this region of enormous dispersion. Okay. I would indicate that inside this region, even the group velocity can be larger than speed of light in vacuum, c. But that should cause no concern still, because of the fact that, in fact, we are going to do the calculation in such a way that when you have you're in this region of in the enormous region of enormous dispersion, in fact, the approximation that I'm going to take in the discussion of the next thing fails, and if the whole thing becomes more involved, and we are not going to that. All right. So what I'm going to tell you, well, so we have been talking about superposition of only two waves. But in order to send a signal from one location to another location, we need to send a pulse of waves. And a pulse of waves, would have to be constructed by the linear combination of waves of all frequencies or of all wave numbers. Let me write it down. Let me start. So you remember phase velocity and group velocity. And now I can erase all this. Let's be careful. All right. Let's talk about a wave. I can propagate it in the positive x direction. So psi of x in time is equal to, that's by convention says that that's the effect of square root 2 pi, integrate over all values of the wave number for each k. The amplitude is of k, then e of I k x minus omega. Omega is not can be thought of as a function of k times t. This amplitude denotes the amplitude for that wave number, and integrate over the whole range of wave number value. Now, let's suppose, in order to proceed, we have to consider certain make certain approximations. Let's assume, and this assumption may not be correct. In fact, it is the fact that this assumption fails in the region of enormous dispersion. That makes the whole discussion of physics in this region very tough. Too tough for us to attack at this point for this class. All right, let's assume that AK is sharply peaked at a certain value of k. Is sharply peaked at k equals k naught. For example, if you put k, A it is sharply peaked at this around this value k naught. If that were so, we can make an expansion of omega as a function of k around the value k equals k naught. So omega k roughly omega at k naught plus derivative d omega by dk evaluated at k naught times k minus k naught plus higher order terms, which I will ignore. All right, then what happens? Then let's see. Okay, omega's here is always multiplied by t, and this term in omega k is independent of k, so can be pulled out of this integration, this one, and so is this one can be taken out of the integration. So the sine of xt will be equal to e to the, oh sorry, this minus this I also. E to the I omega at k naught times time. So this takes care of this. And then this one is minus plus I, d omega by dk, k naught times time. And the rest is back here. 1 over square root 2 pi, dk, ak, what's remaining is e to the I k x, so this, that, and then with, and then this term, in k, is multiplied by this one, so it's minus I, so it's minus, k is outside already, d omega by dk evaluated at k naught multiplied by t. This thing also, this term also multiplied by k, it's both sides. Okay, then minus I omega, and there's nothing left, times 0. I've incorporated this term here for good reason, as you see in the moment, even though there's 0. All right? Now this is a total phase. That's a phase. Okay. Let's assume that energy carried by this wave, in fact, depends upon the square of the absolute square of this wave function. Then, of course, the absolute value of this function is 1. So that the transmission of energy will be independent of this factor. So that's independent by just what's left here. But what's left? If you compare, this wave function given here in terms of this, they look the same, except that, I notice that I have to replace x by this. And replace t by 0. That means this is nothing but the wave function, at, instead of location x, is now location this, x minus d omega by dk times t. And at the time 0. What does that mean? Well, let's plot a wave. Say this is the wave. For the signal. And the time goes downwards. So t equals 0 and t not equal 0. At t equals 0, this is say certain location. This is x. As t goes by, this whole thing would be displaced by this distance. So it will be like this. same shape. With the displacement being given by this, d omega by dk at k naught times time. So that in the amount of time, from t is 0 to t, not 0, okay, the wave has advanced by that much. So this tells me that the speed of propagation is equal to just that, d omega by dk. Lo and behold, this of course is just the group velocity of the wave. So it's the group velocity that determines how fast, okay, energy and accordingly message information carried by that energy propagate. Okay. And we want that speed to be not exceeding c, speed of light in vacuum. That's what we want. And as I will show next time, that I'm going to talk about a case, an example, which will show you that for that system in the example, we'll show that the phase velocity is larger than the speed of light c, whereas the group velocity is less than c. So that's great. That's good. But I should come back to what I'm going to tell you in this diagram. Talk about this region of enormous dispersion. Well, notice that m is a rapid, it changes with omega very rapidly. And in fact it goes down instead of going up. So it has, this region involves a large value of dn by d omega. But the large dn by d omega can be translated as that, in fact, d omega by dk is large. So that means that omega is a rapidly changing function of k, such that this expansion that we have used, and that we use to argue that it is the group velocity that counts, will not hold. Therefore, what we have said, in fact, does not quite explain problems in this region. I told you already, this comes about because we are concentrating on the contribution only coming from the jth resonance. And forget about contributions from others. When you add up the other contributions, in fact, the whole thing goes up. And this curve will not be so. All right? So, I think it's a good place to stop. And next time, I will talk about, one more thing that is contained in chapter 8, I think, yes, in Griffiths, and that has to do with the study of waveguide. Then we talk about transportation of electromagnetic waves inside a certain tube. So we will be talking about electromagnetic waves in confined regions, instead of talking about propagation of the waves in unconfined region. And there we'll find out something very interesting. For example, that the electromagnetic waves in a confined region is no longer transverse, for example. So, and I would talk about an example at the time, and we'll show you. Well, I just told you that the phase velocity can be larger than speed of light c, but the group velocity is not. Hallelujah. Okay, let's stop here.